Okay, hello everyone. Welcome back. How was your day? How was your Chinese New Year? It's still Chinese New Year. This is like which day is this? One, two, three, four, fourth day, right? How was it? Okay.
Okay.
Okay, good. All right. So this is your chapter three. Today we're gonna cover chapter three. There are a lot of slides. I hope that we can cover. Otherwise, we can bring it also tomorrow. Okay. But because there are, as you can see, if you look through your slides, there are about 50 over slides here. Very, very long slides to explain. Okay, can you hear me clear? Okay. Okay, so this is chapter 3, efficiency of algorithm. So you should know how to basically, okay, this is the learning outcome for this chapter. At the end of this lecture, you should be able to, number one, assess the efficiency of a given algorithm, whether that algorithm is written efficiently or not. Okay, and then compare the expected execution times of two methods given the efficiencies of their algorithm. Okay, so this is your learning outcome. Basically, you learn about big O notation, complexity, space, how you execute your the code in your system program. Okay, first thing is this one. This is the first one. Yeah. Okay, hang on. I think this is like a different tab, right? Let's see. Ah, yeah, straight. Okay. Okay, first thing, look at the algorithm one. So in this algorithm, you basically have this pseudocode, like this code, simplified multiplication algorithm. Okay, you have this long first operand, basically indicates this number, and long second operand, you have first and second operand, which gives you this number. So long product is equals to 0, right? For this function, basically operates, manipulates these two operand which you have initialized here, declared. Okay, so long control equals to second operand plus, okay, control more than 0, and then equals to uh, minus minus that particular operand. Product equals to product plus first operand. Okay, and then you have the print line of that product, which is here. Okay, meaning the value that you want after the operation which you executed around here. So when 423 is changed to 100 million, there is a significant delay in seeing the result, because as your value increases, your time of execution for each of your program becomes longer as well. So this is the example of how you have big number operand in this case in your algorithm, and how long it can compute to produce the result. Okay, so sample code is basically is given in this example, multiplication 1 Java. So I have retrieved that from a sample package sample code, and this one is basically showing you multiple um, functions that it is operating here. First section, second section, and then the third section. So how long will that actually operate? Okay, so it's all go back to how you have the number. As your number increases, there is a significant delay in your seeing the result. Okay, this is just an example of your code. Yeah, it's quite similar, but it's just that a while ago it has been, this one has been retrieved to show you how as your number increases, and therefore your execution of time to get the result or the response time also increases. Yeah. So, okay, next one. This is algorithm number 2. Both of this algorithm basically shows you a way on how these algorithms are computed. Like first example is this one. Second algorithm analysis is this one. There's another alternative way to multiply your 7562 and that second operand, which is valued at 423. Okay, so in this example, you are using numbers, okay, integers, compared to the one which you have put inside a while ago. So you use all these characters or string, right? So this is one way. Second way is this. So in this multiplication of the integers or the numbers, you have 4 ways, which I have highlighted here. 1, 2, 3, and 4. So many ways on how you could actually write the code in your program. So it's all of these ways will give you a result whether or not it can compute fast or slow. Okay, so this one, for example, the value which is given here, 7562 multiplied by 423. For first operand multiplied by second operand equals to product of the operands, which means 7562, you can translate this into multiply by 420 and 3, which is derived from this value. Okay, so how do you compute that? Which other way that you can actually compute that? You use this 7562, you multiply by this, that is for first, and you add with the second value, which is this, add with multiply by the second value. Next is the similar, this main first operand, and then you multiply that with the third value, which is derived from here. That is first way. Second way is more bigger value here, but it's simplified in terms of this number. So instead of 400, that 2 zeros will go here, added into this value. So multiply by 4, multiply by 2, because this is 20, that value goes in here. And then the last would be multiply by 3 because it is just 1. Therefore, that is way number 2. Number 3 is more complicated. So this is, I think it is worst case scenario where you have to add every single value 4 times like this. Okay, this is a totally inefficient way of putting in the value of your operand, as in how you put it in your code. Okay, so you must know that if you put a value in your program, the computer actually reads according to binary 0 and 1, and based on, it depends on whether it is linear or non-linear. Linear means one after another, right, in order. Non-linear means it either can go for FIFO or LIFO. So in this case, it matters how you arrange and how you put your operand, first operand, second operand, and how you do the multiplication and put all these operand in order. So the third value, the third way would be that 4 times of this first operand, okay, because you multiply by 4, plus 2 times of this, okay, if you notice, and then 3 times of this. So that is way number 3. Last but not least is that you put arrangement, as in you put this first in the first, and then the second one will be going to the second place, and then the third one is the most value you put at the end. Okay, so that is just a way on how you arrange your operand to be measured in your codings. So this is alternative ways to multiply 7562 and 423. So this is by if it is using a value, right? The first one is using this. Okay, so this is multiplication by using algorithm number 1. So it's basically up to the programmer to actually select which one is more efficient in producing the value or the output that they want to have. Okay, so this is how you want to measure efficiency of the algorithm presented in your code. Next one. So even a simple program can be noticeably inefficient because that is, of course, all the way on how you present it using this method. Okay, this is an example to show you how it will be computed based on the arrangement, linear or non-linear, of the value which you put in here. So, therefore, a program efficiency affects its overall performance, basically referring to the response time of how the result will come out in few seconds, in nanoseconds, in milliseconds. That counts, okay? Based on how you arrange your operands or whatever value or whatever you call it, the execution of your algorithm in your code. Okay, that's why as a programmer, it is very essential to learn what is the best way, best practices on how you arrange your code. Okay, so how can we measure efficiency so that we can compare the efficiency of various approaches to solve a problem? So there are many approaches to solve this kind of measuring how you want to see that your code can be presented efficiently. We're going to cover that here. There are two ways. One is experimental studies. Second one is analysis of algorithm. Experimental is basically, okay, no, this is video first. Okay, hang on now. Experimental study is none other than you find several other codes and then you check which particular codes that runs better, gives efficient running time, response time, in accordance to how your codes are written. Okay, analysis of algorithm is none other than if you put yourself in, you cut one portion of that algorithm and you analyze. If you run that algorithm, how would that response time would be, shorter or longer? Okay, that's analysis of algorithm. Okay, so this is algorithm efficiency, algorithm and efficiency. Um, Briefly by this guy, we can watch this so that it would be a bit clear to see, right?
Welcome. Today I want to give you an introduction to algorithms with a focus on efficiency. So how fast is our algorithm, and in particular, how can we analyze how fast the algorithm is? And we're going to do that by the example of linear search. But let's first have a look at what's an algorithm. And where do we use algorithms? We use algorithms in everyday life. For instance, when we do route planning. So route planning essentially boils down to finding shortest path and using a shortest path algorithm. Searching the internet. Information that we're searching will have been heavily pre-processed using sophisticated algorithms. When we analyze data, we also use dedicated algorithms for that. For instance, clustering algorithms, or for classification nearest neighbor algorithms. So we use algorithms for all kinds of things every day, and also on all kinds of devices. So we're not only using algorithms on a computer, but for instance, in the route planning setting, in the car, or on the smartphone, and so on. So algorithms are everywhere. But what is an algorithm? So let's first start with this somewhat kind of general definition, saying that an algorithm is a well-defined computational procedure. So well-defined meaning that it is clearly specified what it does, and it takes some input, so some value or set of values as input, and produces an output based on that. That's an algorithm. In short, we look at algorithms as sequences of computational steps that go from the input to the desired output. And when we talk about algorithms, we very often have to talk also about data structures. So when we want to have, in particular, when we want to have fast algorithms, we often have to think about how do we store the data so that we can allow those fast algorithms. And a data structure is simply the way that we store and organize the data so that we can efficiently perform the operations that we want to perform, also modify the data. And when we talk about data structures, we like to separate functionality from the actual implementation. So the functionality, that's what we call then the abstract data type. So that just says, okay, these operations we want to support. And then the implementation realizes those operations and tells us how are we storing the data, but also implement. Today, we're not going to talk about data structures, but very often when we have algorithms, we also have to think about the data structure. So that's why that's here already. Back to algorithms. What do we expect from an algorithm? So with an algorithm, we want to solve a computational problem. So for starters, this computational problem will have to be well specified, requires a well-specified input and output. What do I mean by that? Let's take an example. Here's a problem. Is that well specified? Given a collection of values, find a certain value x. So that in several ways is not well specified, both in terms of the input and the output. So in terms of the input, a collection of values, okay, you might also ask what kind of values, but first of all, the question is also what kind of collection. A common way to store data would be in an array. So here you see an array. What is an array? It's a sequential collection of elements. So we have these elements in sequence. So we can count them 0, 1, 2, 3. So they're stored in such a way that we have constant time access to an element via its index. So if you tell me I would like to have the element with index 5, then in constant time, your array can tell you that's 12. Okay, so that's a way to store data. This comes close to Python list is. So later in the course, we're actually going to see how arrays and Python lists exactly relate, but for now, you can think of them as being very similar. So that's how we're given the values. Also, x should be part of the input. But then there's also this issue with the output, as in this statement doesn't even tell us what the output is. It just says the algorithm finds something. But what does it with after finding something? Does it return anything? Does it return x? Returning x is not very useful because we already inputted x. I mean, that can't really have been what we were looking for. What we really want to know is where is x in the collection? Or first of all, actually, whether x is in the collection. And then if x is not in the collection, we also need to return something. So this is now a well-specified input and output specification for the problem we wanted to define here. Given array A of elements together with an element x, we want to output either an index I such that the element at that index is x. So if x is 12 in this case, I would want to get as output 5. Or if that element doesn't exist, the algorithm should report that it can't find that element, or more specifically, that element is not in my array. Okay. I wanted to talk about what do we expect from an algorithm. So far, we just know what we said what a computational problem is. What do we want from an algorithm? Essentially, there are two things that are most important to us. The first is maybe even too obvious, but very important and something that we always have to carefully check, in particular for more complex algorithms, and that is that this algorithm is actually correct. Output. Of course, if the algorithm isn't correct, it's not really, no matter how fast. Secondly, the algorithm should use resources efficiently. So let's first briefly talk about correctness. So an algorithm produce correct output. Of course, there might be settings not clear what that means. For instance, in the route planning setting, I mean, I could say correct output is if the travel time is actually shortest, but that depends on how the traffic. There might be problems where it's not even clear what the correct solution is. So here, if I want to do character recognition, okay, it looks like an S, but how do I know? The problems that we're going to look at, there we will always have a clear, correct solution. So you don't have to worry about these cases above. Whatever problem we're looking at, there it is very clear what the correct output is. For instance, if I say I want to have the index of an element in an array, it's clear that what it means to give back a correct index. As a side remark, not all types of algorithms focus on being correct all the time. So for instance, randomized algorithms, you can ask for algorithms that are correct with high probability, or approximation algorithms where you say, okay, you don't have to have exactly the correct solution, but it should be close to it. For instance, you don't need to have the shortest path, but a path that is not much longer than the shortest path. But again, those are not algorithms we're focusing on here. We are going to focus on algorithms where there is a clear, correct solution, and we aim to get that correct solution. So much about correctness. Efficiency. An algorithm should use resources efficiently, and that could mean many things. Our focus is on time. So the next most common aspect to look at is memory. Obviously, memory efficiency is also important. I mean, if you're time efficient, then at least to some extent, often you're also memory efficient because you cannot use more memory than you're spending time. But sometimes you also have to look at memory. Half is on time. And then there are also other resources like network bandwidth, which depending on the setting of where you are developing your algorithm might be very important. And then that's a resource that you should be analyzing. So since we're focusing on time, the question is, how do we measure time? And the natural first idea might be to say, let's implement the algorithm and test it and see how fast it runs. So let's have an example for that here. So what I did here was I was testing how fast can I test whether an element X is in a certain collection. Let's call that collection A. And what you see here is a plot where on this axis you have the size of, and on the other axis the running time. And then depending, so this is actually more a data structure question nearly, or not only nearly, it's a data structure question. Depending on how I store my data, whether it's a Python list or a Python set, and you don't need to know what that is right now. It's just two different ways to store data for the purpose of this slide. We get very different running times. So one looks more linear, one looks somewhat constant. But I mean, I can also only say it looks linear and it looks constant, and it is this, or seems to be this for these specific inputs. But I have to be careful when I want to generalize this. And okay, so this is a useful type of analysis. This is not what we're going to do because it is difficult to make general conclusions from these types of experiments. So one problem is in many ways, the running time depends not only on the algorithm, so the running time of experiments not only on the algorithm, but on lots of factors that have nothing to do with the algorithm. For instance, the computer system, also the programming language will have a huge impact on how fast your algorithm runs, the compiler, my skill as a programmer, whether there are other programs running in the background, and so on. Also, the running time that I'm measuring will very much depend on the data sets that I'm testing. So the statements that I'm making are really just about that data set. So instead of doing experiments, we are going to focus on a mathematical analysis of the running time. And this analysis will have two components. So for one, we're going to look at the running time as a function of the input size. So we're saying, okay, the running time is a function t of n of the input size. And then we're focusing on a specific aspect of that function, and that is the growth rate. This in particular means I'm really just looking at the dominant term. So I want to say something like, okay, the running time is constant, the running time is linear in the input size or quadratic, whatever it is. Let's take an example. And let me say, we're not going to count machine cycles beyond this slide. It's just, or this, at this point, a good way to formulate what time might be. But we're not going to do that later. Anyway, let's say I have an algorithm A. It needs 50n plus 125 machine cycles to search a list. Then, first of all, we can observe that the 125 doesn't really matter for large data. I mean, already, if for instance, n at the point where n is 3, 50 times 3, 150 is already larger than 125. At the latest, when n is 100, the contribution of the 125 will be very minor. So what I'm really interested in is the linear growth of the running time here. And I'm also not so much interested in the 50, because the 50, again, might depend on all kinds of things. In particular, in terms of running time, if it's really time, it will depend on the programming language, or it will depend on the computer system. While the n is really something that comes from our algorithm. So let's take another example. Here we have another algorithm with this running time. If I'm focusing on the order of growth, I'm looking at the dominant term, and I'm going to ignore the factor in front of it. So I take the dominant term, that means I'm ignoring the quadratic term, the linear term, the constant term, and from the dominant term, I'm also just interested in this n cubed, not in the 20. So this algorithm grows, so t of n grows of order n cubed. We want to compare growth rates next by some examples. For that, we have to look a bit more at different types of functions. So let's do that. Logarithms often show up in the context of algorithms. Let's say I take the logarithm of n to the 35. How does that compare to square root of n? So the logarithm is the inverse of the exponential function. So just as we know that the exponential function goes very fast, the logarithm actually goes very slow. And even if I take a high exponent, eventually something like square root of n will be faster. So this will be growing faster, will dominate any logarithmic terms. So generally speaking, logarithmic functions grow slower than polynomial functions, making this more formal. No matter what a is here, and no matter what b is here, as long as both are positive, log a to the n goes slower than n to the b. Likewise, if I'm comparing polynomial functions with exponential functions, then there it might be more intuitive. Exponential functions grow faster, even if I have a high exponent here in the polynomial function. Now, polynomial functions go slower than exponential functions, or formally speaking here, n to the a goes slower than b to the n for any positive a, okay, and b larger than 1, because if b is smaller than 1, actually this is not a growing function, but it goes to, if it's between 0 and 1, it will go to 0. And since we've been speaking about logarithms here, just as a reminder, in this class we're going to use logarithms quite a bit, and there are these rules about logarithms, which you know, and I don't want to go into detail here, but you can, if you want to look at them again, pause the video. The only important thing to note here is that if we are talking about logarithms, we're always going to talk about logarithms base 2. And that comes from the fact that in terms of, in computer or in the analysis of algorithms, it's very often the base 2 logarithm that is relevant. Good. So I want to put that into use in a quiz soon, but let me first wrap up a bit more further. When we describe an algorithm, so we talked about requirements. So when we now describe an algorithm, these will also be the aspects that we're focusing on. The complete description of an algorithm will have 3 components. One is the algorithm itself, so a kind of description of the algorithm. And the description will be in whatever way is clearest and most concise. So if I'm describing an algorithm in the context of this course, doesn't have to be an implemented algorithm. So you don't have to give me code.
Okay, this explanation is very long. Okay, you can watch it on your own later on. Okay, we're going to go towards the next slide. Yeah. This is basically telling about algorithm efficiency and how you manipulate all the description on how data should be presented in your program based on the functions. Okay, but I will not get you into that. It's too long. Let's get on with another one. Yeah. Okay, so I mentioned here there are 2 ways to measure efficiency of algorithm. One is experimental, another one is analysis. Now let's move on to the first one, which is experimental studies. Experimental studies basically none other than just to implement the algorithm, okay, and then to see whether or not the program, running the program on various test inputs, you have a set of functions, you have a set of okay, see, you have a set of instruction, which you have here, all right? So this requires that you enter the value, and if the value equals to the product plus first operand. Okay, so basically you need to input as much value as possible in order to get whatever you want for that product. So same goes with this experimental studies. You run the program on various test inputs, while at the same time you record the time spent during each of the execution to get your expected output. How long does it take to come to the conclusion of displaying your results? Okay. In this example, collecting running times in Java, we use this method called system.current time meals. Meal is. So this one actually record the time immediately before executing the algorithm and then immediately after that. So how long is the elapsed time? So it will compute the difference between those times to obtain your elapsed time, or in this case, it's referring to your actual time taken to execute one simple program, or one program that has several logic of the execution that you need to, conditions that you need to fulfill, and until the end of that condition, whether it is finally fulfilling that condition. Okay, so that is the difference between those times to obtain the elapsed time, actual time taken to complete the whole cycle of executing the program. So, example here, this is a code fragment for timing an algorithm in Java. So you have long start time. This is the basically formula. Start time equals to system dot current time, the current time which you put in, and then end time would be the current time. Long end time would be the current time, system dot current time mils, okay, and then long elapsed is equal to end time minus start time. All right, start and end time means start time is the current time before it starts. End time would be the time, the current time after it's executed, and long elapsed means actual time would be your end time, okay, which is here minus your start time. So obviously you get what is your actual time spent. Okay, so that again is given in this example, timing algorithm merely.java. In this example, it produces operations of counting the execution of time based on nanoseconds. It's not millisecond, it's nano. Nano means more faster than milliseconds, yeah? So if you look at the example, it is basically calculated here, okay? And then again, it calls a function and calculate the same thing until the end, this side. All right, so until it gives you a result, which is algorithm number 2 and algorithm number 1. So there are basically 2 algorithms which you process here, which gives you the first operand, which you need to input 7562, and then of 100 million values that you can put in. So 2 values you need to test, meaning before you want to test how long will this basically compute, to give you the end time of each operation, you have to enter a value of between this and this, okay? So that is basically experimental. So experimental method also, we are interested in the general dependence on running time and on the size and structure of the input. Okay, so you actually all in this code, the most important thing is that the more value, the bigger the value, therefore to execute, okay, or the more arrays of values that you put in, the more time that you will spend, or the more time that the program spend in trying to execute the program and to find what value that it needs to display. Okay, so experimental means you're just merely trying to check how big is the input and how big is the output, how big is the input, and then how long will that particular size affect your runtime. Okay, so we should perform independent experiments on many different test inputs on various sizes, okay, from small to large. So then only that you can visualize the results by plotting the performance of each run. Okay, you have a set of values that you need to test in that particular program. So based on that particular input that you put in, you can actually plot the response time or the execution time that it takes a program to complete based on the value that you have inserted. Okay, so that is how you can visualize the results by plotting the performance of each run of the algorithm as point with x coordinates, okay, and equals to the input size of y coordinate, x and y, and then you plot, okay. So such visualization provides some intuition, okay, because now you're doing experiment on which particular input gives a shorter time of running the execution of that particular program. So you test the data one by one. Therefore, it gives you a sort of intuition regarding the relationship between the problem size, which is the size or of the input, and the time for the input to execute and complete the whole search if you were to search for data inside that particular program. until the main results that you are looking for is displayed. So you want to find out, you want to experiment. Okay, this is experimental method. So then after that, after you plot, you are using that particular data to produce a statistical analysis to find out the best fits function of the input size to the experimental data. That means you know that if after you have put in all the basic inputs that you need to experiment, you know after that which produces the best solution to how much data, or which size is appropriate to which particular time. And then that leads you to find, you're able to find a way on how you're going to present your data in the future, as in how would you want to write your function in your program. So to be meaningful, this analysis basically requires that you choose a good sample of inputs and test enough of them to be able to make accurate statistical claim about the algorithm running time. Make sense?
Hi.
Yeah, makes sense. Because if you are a programmer, you basically need to find the best solution how to present the data and what are the kind of conditions for you to basically get the output of your program, rather than there are inefficient way of presenting that, which I've shown you earlier, how you multiply first operand, second operand, and then or the numbers which you want to calculate. So you choose which way is the most suitable in this experimental method. After you have done everything, then you will derive a result that gives you a good sample of inputs to test which particular way that is fitting to producing efficient allocation of time, and also how you present that in your particular program. That's experimental. So what are the challenges of experimental analysis? Experimental running times of two algorithms are difficult to directly compare unless the experiments are performed in the same hardware and software environments. Okay, just like when that man is actually mentioning in this video, saying that sometimes when you run your program in a different machine, okay, you tend to get different kind of results because you get affected by the kind of environment that you are in for your system. Sometimes there is a problem with that computer running time, processing time, that as well as affect that changes in your execution of your algorithms. Okay, unless if that A and B algorithm are able to be performed in the same hardware and software environment, then therefore you are able to actually visualize exactly whether or not these particular comparisons are made accurately. Okay, so experiment, that is one challenge. Another one is experiment can be done only on a limited set of test inputs. Because you want to make as much coverage as possible, it is advisable that you want to put in as much input as possible. But usually when you do testing, there are so many possible values that you put, and you require time to do that. Okay, so that is another issue, because sometimes the tester doesn't have that, cannot afford to have that test to just merely do this kind of what do you call the experiment. So therefore they need to test every single input that requires time. So because of that, sometimes they left out, maybe accidentally, because of time constraint. So because of that, you tend to not able to get accurate result for your experiment. Okay, because there are inputs that are not basically tested. So probably these input which have been left out could be important. Therefore, this is kind of a limitation for experimental. It takes and consume time. All right, next one. An algorithm must be fully implemented in order to execute it to study its running time experimentally. Yeah, okay. So like I said, same goes with your input. Algorithm has to be fully implemented, okay? Sometimes you want to test only one particular function or one particular module. So in order to actually execute or know that the whole basic programs works as it should and gives you the time that you want to have an efficiency when you want to write your code. Therefore, it has to be executed fully. Every single line has to be executed, has to be tested, has to be run, compiled together to execute it, to study its running time, whether it is producing the efficient algorithm, okay, for experimental analysis. That's why it says an algorithm must be fully implemented in order to execute execute it to study its running time experimentally. So again, it is time consuming. So these are one of the challenges of experimental analysis. Next one is your analysis of algorithm. Analysis of algorithm is basically checking your checking your codes, yeah? Checking process of measuring the complexity of an algorithm. All right, so there are basically types of complexity is stated by number one, space complexity. What is space complexity? Memory, which are required to execute the code. Or this is another elaboration, the amount of memory used by algorithm, which includes the input values to that algorithm to execute and produce the result. That is space. How much memory is particularly used in order to run that particular program? Space. Okay. Next one is your time complexity. Is none other than looking at the time the code takes to execute. How long? 1 second, 2 seconds. You know, sometimes if there's a problem with your computer, it takes longer time. Like what I have experienced, I was trying to run my NetBeans IDE the other day, and it takes longer than expected because something happened to my laptop. So it takes longer. So that is basically depending on the external hardware as well. So time complexity is the time the code takes to execute. Or, in other words, it is the amount of time taken by a given code or algorithm to process or run as a function of the amount of input which is inserted into the code, as in the function you insert into that program, what it runs, what required that kind of input, and then you put it in. In other words, time complexity is essentially efficiency. How fast can you get the output? Because when you write a code, you simply just want to see whether your code runs. You want to see whether that operation in the condition that you put inside the code working. It gives you the output of what you wanted. So time complexity. Okay, how long a program function takes to process a given input. All right, so there is usually a trade-off between time and space requirement of a program. There are ways on how to solve that problem. Hang on, what is this? Yeah. Okay, that particular question, which is this one, is I think I gave brief explanation about that in the next code, next slide. Okay, so but in the meantime, before that, there is also a question of what is big O notation in brief. Before you go towards the next slide, more and more we're going to go towards the notation that is essential in analyzing your algorithm. So this is an overview, which I have in this video, about introduction to a big O notation and a little bit about time complexity. Okay, so let's just watch. I think this is shorter than the one previously.
Hey everyone, in this video, I'm going to give you an introduction to big O notation and time complexity. These concepts basically give you one way of describing how the time it takes to run your function grows as the size of the input grows. To see what I mean by that exactly, let's take a look at a few examples here. First of all, let's say you're given an array like this, and let's say that this array could be any length. It could be 100 elements long, 1,000 elements long, or even 100,000 elements. And let's say you want to write a function that takes this array and returns the sum of all the numbers in this array. So in your function, you want to add up all the numbers in this array and return the sum. And that function might look like this function right here. And I'm going to use pseudocode here to write this function. So first of all, let's define our function that's going to be called findSum, which is going to take given array as the input. And then inside this function, first of all, we're going to initialize a variable called total to 0. And then for each I in this given array, or for each number, each of these numbers in the given array, add that number I to total. And then at the end of this function, we're just going to return total. And that way, we'll be able to find the sum of all the numbers in this array. Now, when you write this function in whatever language you're using, whether it's Python, Java, or anything else, you might ask yourself, well, how much time does it take to run this function? And that's actually a really hard question to answer because it depends on so many different factors. For example, how fast is your computer? And when you run this function, are you running other programs at the same time? And also, which programming language are you using? So instead of asking this question directly, you might ask a related question instead, which is easier to answer actually. And that's, how does the runtime of this function grow as the size of the input grows? And this is a valid question to answer because depending on the size of the input, or depending on how many elements there are in the given array, it's going to take different amounts of time to execute this function. Because the more elements there are in the given array, the more elements there are to add up and find the sum for. And to answer this second question, you can use a pair of tools called big O notation and time complexity. But before we get into that, I actually ended up running some experiments in Python to see how much time this function actually takes to complete for inputs of various sizes. So let's take a look at the results of that first, because that's going to actually help us explain the concepts of big O notation and time complexity. So here's what I did. I took this function and then implemented it in Python. And then I generated a bunch of arrays with random elements with various sizes to use as input. So for example, those arrays might look like these if the size is 5, or these if the number of elements in the array is 10. And using these randomly generated arrays as input, I ran this function findSum many times to find the average time it takes to run this function for each n, where n is the size of the given array, or the number of elements in the given array. So if the given array is this one, n would be 5, and if the given array is this one, n would be 10. And here's the result I got. On the x-axis, you see the size of the input, or n, and the size of the input ranges from 1 element, 2 elements, and so on, up to 30 elements. And what you see on the y-axis is the time it takes, the time it took to run this function on average in microsecond. So for example, with 1 element, it took about 0.2 microseconds to run this function. And then with 30 elements, it takes about 1.25 microseconds on average. And as you can see, there's this straight line-like pattern, or a linear pattern here. Or in other words, as the size, or n, increases, the amount of time it takes to complete this function increases linearly or like a straight line. And this pattern is called linear time complexity because again, as the size of the input increases, the time increases linearly. So basically, time complexity is a way of showing how the time it takes to complete a function or a particular piece of code increases as the size of the input increases. And linear time is just one type of time complexity, and there are many different types. For example, constant time. This is when the time it takes to complete a function does not increase at all as the size of the input increases, or when the time stays at constant. So in that case, the graph might look like this. And there's also quadratic time complexity. And that's when the time it takes to complete a function increases like a quadratic function. So that might look like this instead of the linear function that we saw earlier. Now, expressing different types of time complexity with words like linear, constant, and quadratic is a little bit cumbersome, partly because you need to remember to use these different words. So you might say, is there any way to express different types of time complexity in a more mathematical, systematic way? There is, and that's what big O notation is. So for example, linear time can be expressed as big O of n. That's capital O followed by parentheses with n inside. And n is usually the size of the input, and in this particular case, it's the number of elements in the given array. This whole is either big O of n or simply O of n. And constant time can be expressed as big O of 1, and quadratic time can be expressed as big O of n squared. So as you can see, just by changing what's inside the big O expression, you're able to express different types of time complexity. But how do we know that linear time should be big O of n and constant time is big O of 1, and so on? Well, to understand, let's take a look at the example we saw just earlier where we had linear time, or this graph right here. Now, just by looking at this graph, you can probably tell that the time it takes to run this function, or t, can be expressed as a linear function. So that should be in the form of t equals n plus b, where n is the size of the input or the number of elements in the array, and a and b are two constants. And how do we know that this expression is big O of n? Well, to find that out, there's a simple trick for doing that, and there are two steps you need to follow. The first step is to find the fastest growing term in the given function. So we're given an plus b, and here we have two terms, an and b. So you need to ask yourself which one is the fastest growing term. Well, b does not grow at all as n increases, so the fastest growing term here is an. And then the second step is to take out the coefficient out of that fastest growing term. So the coefficient here is a, because a is a constant and n is not a constant. So if you take out the coefficient out of this term an, you're left with just n. And that's what should go inside the big O expression. Okay, and a quick note here. This is actually not the most mathematically rigorous way of finding the big O expression, but it's actually good enough for all practical purposes. But if you want me to make a separate video about the formal mathematical definition of big O, let me know in a comment. Anyway, let's take a look at another example here. What if the time it takes to run your function, or t, turns out to have this form, cn squared plus dn plus e, where c, d, and e are constants? Then you can follow exactly the same steps. First of all, find the fastest growing term. There are three terms here, cn squared, dn, and e. And immediately you can tell that e is not the fastest growing term because it's just a constant. So you need to compare cn squared and dn and find which one is the faster growing term. One way to do that is by drawing them on a graph. So dn will look like this, or maybe this, depending on the value of d. It's just a straight line. And Cn squared will look like this, or maybe this, or maybe this, depending on the value of C. And as you're examining these two expressions this way, you'll notice that no matter what the values of C and D are, eventually as n gets larger and larger, Cn squared will be much bigger than Dn, and it'll keep getting bigger and bigger. And that's how we know that the first term, Cn squared, is the fastest growing term here. So basically, we're looking for the fastest growing term when n is very, very large. So here, as long as C and D are both constants and positive, we'll know that Cn squared is the fastest growing term when n is very large. So you can take Cn squared as the fastest growing term out of step 1 and then go to step 2. Take out the coefficient. The coefficient here is C, so take that out, and what's left here is just n squared. And that's what's going to be inside the big O expression. So we have t is big O of n squared, and that's what we have here, quadratic time. Okay, so one thing that's convenient about time complexity and big O notation is that they give you a rough idea about how your function scales as the input to that function gets larger and larger. And in computer science, you tend to care more about the larger input than smaller input, because when for example, I ran this experiment on my new MacBook Pro, which is pretty fast, and
Sorry, no sound?
The sound on and off.
Wait a second. Wait a sec, yeah. Something going on. Let me just figure this out for a second here.
no matter how fast or slow your computer is, and pretty much no matter what programming language you use, as long as you use the same algorithm or the same steps for solving the problem, you'll still get the same time complexity and the same big O.
Okay.
Okay, for more practice, let's take a look at another example here. Here, just like the previous example, we're given an array of numbers, and this could be any size. And here we have a function called stupid function, which takes the given array. And this function is stupid because this is all it does. It initializes a new variable called total, and then it returns it. So it doesn't really do anything with the given input. And I ran the same experiment as the previous example using this function. I took this function, implemented it in Python, and then ran this function for arrays of various sizes, and found the average time it took to execute this function for each of those inputs. And here's the result I got. And just like before, we have n, or the number of items, the number of elements in the given array on the x-axis, and on the y-axis, we have t, or the average time it took to run this function for each n. And as you can see, the time it took to run this function doesn't increase at all as the number of elements in the array increases, which makes sense because this function doesn't do anything with the given array. Okay, so you can express t here, the time it takes to run this function, as a constant. Let's call that constant c for now. And in this particular case, c here is about 0.115 microseconds. And here you might say, how can we express this with big O? To find that, you can basically follow the same two steps that we saw earlier. So first of all, find the fastest growing term out of this expression. We only have one term here, 0.115, so that's automatically the fastest growing term here. And the second step is to take out the coefficient. But this whole thing is a coefficient. So how should we think about it? One way to think about it is that 0.115 can be rewritten as 0.115 times 1. So when you take out 0.115 out of this expression, you're left with 1. So you get t is big O of 1. This is actually equivalent to big O of 2, big O of 3, big O of 0.115, and so on. And you can technically choose any of those numbers, but by convention, we usually use 1 here inside the big O expression. And this is, of course, constant time, because the time here is constant. Now, let's say you have two functions solving the same problem. Not necessarily something stupid like this, but a problem that's more meaningful, something that you actually want to solve. And let's say you wrote two functions for solving that problem. And one of them happens to take only constant time, so the graph looks like this. And the other one takes linear time, so the graph might look like this that we saw earlier. And so the first function takes big O of 1 in time, and the second function takes big O of n in time, where n is the size of the input, and they solve the same problem. And once you compare these two functions, it'll be clear that the second function will take more time when n is large enough, regardless of where the constant is. So if the constant is here, as in the graph, or here, here, or here, when n is large enough, the second function takes more time. So as you can see from that example, another benefit of using big O notation and time complexity is that they allow you to quickly compare multiple functions in terms of their performance. In this particular example, if you can achieve the same thing, constant time is probably better than linear time, or O of 1 is better than O of n. Now, time complexity is not the only factor that you should consider when you're trying to decide between multiple potential solutions for a single problem. For example, you should consider how easy it is to read your code and how much memory each of your potential functions consumes, but time complexity is definitely one of the factors that you should consider. Okay, so far, what we've done to find the time complexity and the big O of a given function is that we run this function many times for many different inputs, and then we found the average time it takes to run this function for each size of the input. We plotted the results on the graph, and then using those graphs, we found the time complexity and big O. But that's actually a lot of work to, conduct an experiment every time we have a function. So is there any way to find the time complexity and big O without running an experiment? There is, so let's take a look. Here, just like before, we have the stupid function, which takes the given array, and in this function, we initialize the total variable to 0, and then we return that variable. Now, what if we didn't know the time complexity of this function yet, and we wanted to find it without running any experiments? Well, the first step for doing that would be to consider each of these lines, and then ask yourself, how much time does it take to execute each of these lines? Well, let's take a look at the first line. This line initializes a variable called total, and then assigns the number 0 to that variable. If you think about it, it doesn't depend on the given array at all because we're just assigning the same number every time. So no matter how big or small the given array is, this line should take pretty much the same amount of time every time. So it should take a constant amount of time every time. Or in other words, the time it takes to execute this line is big O of 1. And similarly for the second line, we're returning the same number every time, which is 0 in this case. So it should take a constant amount of time every time as well, no matter how big or small the given array is. So the runtime of the second line is also O of 1. And here, what's nice about big O is that once you have these, big O expressions for each of these lines in a function, you can just add all of them up to find the total amount of time it takes to run this entire function. So let's do that right here. Let's call t the time it takes to run this entire function, stupid function, and that's going to be O of 1 plus O of 1. And to find the sum of these two big O expressions, you can just go back to what O of 1 is. And if you remember from the previous section, O of 1 is just saying t is the sum of two constants, whatever those constants are. So you can, for example, rewrite this as c1 plus c2 by calling the first constant c1 and the second constant c2. So I just rewrote t as c1 plus c2. And then once you add up two constants, you get another constant. Let's just call that c3. And so what we found just here is that t is just a constant, which we're calling c3 here. And then as we saw earlier, we can rewrite c3, a constant, as c3 times 1. And then we have only one term here. So this is the fastest growing term out of this time t. So we can just take out the coefficient c3, and what we get is just O of 1. So what you just found here is that when you have two constant time, O of 1 and O of 1, you just get O of 1 back. And that's generally true as well. So O of 1 plus O of 1 is equal to O of 1 in general. Anyway, let's take a look at another example here.
So in December 2017, I was at 77 kg and 35% body fat. Nothing seemed to have worked for me. I had tried.
Here we have the first example we saw earlier, find sum, which takes given array as the input. And then in the function, first of all, we initialize total to 0. And then we run a for loop for each I in given array, or for each number in the given array. And then in the for loop, we say add I, or each of those numbers, to total. And at the end of the function, we return total. And that way we can find the sum of all the numbers in the given array. And what if we wanted to find the time complexity and big O of this function? To do that, we can go through the steps. So look at each line and think about how much time it takes to execute each of those lines. So total equals 0. It's the same as before. It only takes a constant amount of time, or big O of 1. And return total, the last line, is the same thing, just O of 1. And if you look at inside this for loop, total plus equals I, we're just adding up a number, a single number, to total. And assuming that the range is fairly reasonable, let's say I is always somewhere between, 0 to 10, this operation actually takes roughly the same amount of time every time, or a constant amount of time every time, no matter how big or small the given array is. So this line actually only takes big O of 1 as well. And then if you want to be a little bit more rigorous about this, you can also think about how much time setting up this for loop takes, and that's actually O of 1 as well. And once you have all of that, you can just add them up to find the total amount of time it takes to execute this entire function, find sum. So let's call that time t2. And that's going to be something like this, O of 1 plus n times O of 1 plus O of 1. So these two O of 1s at the beginning and at the end come from these two lines. You could add another O of 1 if you want to be a little bit more rigorous for setting up the for loop right here. And then between these two O of 1s, we have n times O of 1 because we have this line right here, which takes O of 1. And we need to execute this line n times because we need to repeat this process, adding I to total n times, where n is the number of items in the given array. And that's why we have n times big O of 1 here. So adding that all up, we get t2 is O of 1 plus n times O of 1 plus O of 1. And to find what this whole expression should be in the end, we just need to go back to, just like before, what O of 1 stands for. And it stands for a constant. And here we have a bunch of O of 1s, 2 or 3 depending on how you count them. And when you add up a bunch of O of 1s or a bunch of constants, you just get another constant. So let's call that constant C4. And then for this O of 1, let's call this constant C5. So we get this whole expression, T2 is equal to C4, a constant, plus n times C5, which is another constant. And to find the big O expression that fits this whole expression, C4 plus n times C5, we can just follow the same steps that we reviewed earlier. So first of all, find the fastest growing term out of these two terms. We only have two terms here, C4 and n times C5. And the fastest growing term here is n times C5 because that term actually grows as n grows larger. But C4 doesn't change because it's just a constant. So the fastest growing term here is n times C5. And the second step is removing the coefficient, which is C5. And once we do that, we get n. And that's what should go inside the big O expression. So we get this is O of n. So we just found that the time it takes to execute this function, find sum, t2 is actually O of n, or it's linear time. Okay, let's take a look at another example here. And this time, we're given a different kind of input. We're going to call it array 2D, and this is going to be a two-dimensional array. A two-dimensional array is basically an array of arrays, and it might look like this, for example. So this is an array of 3 arrays. So this is an array, and the first element of this array is this array right here, 1, 4, and 3. And then the second element of the outer array is this second array right here, 3, 1, and 9. And then in total, we have 9 elements, as you can see here, or 9 numbers. And another example might look like this. This time, this is an array of 4 arrays. So we have an array here, and then the first element of this array is this array right here with the elements 1, 4, 3, and 1. And the second element of this entire array is this array, and the third element is this array, and the fourth element is this array. And then in total, we have 16 numbers in this entire array. And then let's say that we are always given a square two-dimensional array, which means that the number of columns is the same as the number of rows. And let's call the number of rows n. So that means that we have n columns and n rows in this given two-dimensional array. So we have n squared elements in the two-dimensional array. And let's say we want to write a function that takes one of these two-dimensional square arrays and then finds the sum of all the numbers inside the two-dimensional array. And that function might look like this. Let's call this function find sum 2D. and then it's going to take the given two-dimensional array as input. And in this function, first of all, we're going to define a new variable called total, and then assign number 0 to it. And then we're going to run a for loop, actually a double for loop. And we'll say for each row in this two-dimensional array. So that's, for example, if you're given this array right here, when I say for each row, I'm referring to this row, this row, this row, and then this row. And then in each of those rows, for each I, or for each number. So if we're looking at, let's say, this second row right here, or the second array right here, each number would be this number, this number, this number, and then this number. We want to add I, or each of those numbers, to total. So we just wrote total plus equals I here. And then at the end of this function, or after we're done with this double for loop, we're going to return total. And that way we'll be able to find the sum of all the numbers in the given two-dimensional array and then return that number. And here, to find the time complexity and big O notation of this function, find sum 2D, we can go through the same process as the one we saw just earlier. So let's take a look at the first line here, total equals 0, defining a new variable called total, and then assigning number 0 to it. It only takes a constant amount of time. It doesn't depend on the size of the input, so that's O of 1. And then the last line right here, returning the total number, this is only going to take a constant amount of time as well, so that's O of 1 as well. And this is assuming that the total, the sum of all the numbers in the given array, is reasonably small. And what I mean by that is that it's small enough so that it fits in a single integer variable, for example. And then once you examine this line right here, total plus equals I, that only takes a constant amount of time as well, or it doesn't depend on the size of the input. Adding a number each time I to total should take roughly the same amount of time every time, regardless of how big or small the given array is. So that's also big O of 1. And to find the total amount of time it takes to execute this function, you just need to them this argument just a little bit here. Anyway, let's call the time it takes to execute this whole function t3. And that's going to be O of 1 plus n squared times O of 1 plus O of 1. These two O of 1s at the beginning and at the end come from these two lines at the beginning and at the end of this function. And then this O of 1 come this line right here within the double for loop. And this line, total plus equals I, we need to repeat it n squared times because there are n squared elements in the given two-dimensional array. So the total amount of time it takes to go through this entire double for loop is actually n squared times O of 1. And that's actually where I'm simplifying this argument a little bit here, because it takes some overhead to set up each of these for loops. And I'm not accounting for that here. And that's actually okay here. If you want to account for that, you can add extras like, an extra O of 1 or n times O of 1. And when you do, you will see that the result is going to be exactly the same. But anyway, let's go with the simplified argument. To compute this whole expression, let's go back to the definition of O of 1. That was just a constant. So we have two constants here. Adding two constants up, we get another constant. Let's call that constant C6 right here. And then let's call this O of 1, this constant right here, C7. So we get T3 is C6 plus n squared times C7, where C6 and C7 are constants. And then we can go through the same two-step process that we used earlier. First, find the fastest growing term. That's this term right here, n squared times C7. And then we need to remove the coefficient. That's C7. So n squared is what should go inside the big O expression. So we get this is O of n squared. And so the time it takes to execute this entire function, find sum 2D, which is T3 is O of n squared. And that's quadratic time complexity. Okay, so that's basically how you can go about finding the time complexity, which can be expressed as a big O notation like this one. you had 2 double for loops. And those double for loops, let's say, do exactly the same thing. How would that affect the big O notation and the time complexity? You might say, that new time, let's call it T4, is going to be of 2n squared because we need to repeat that double for loop twice, but that's actually equivalent to of n squared. Let's see why that's the case. If we know that T4 is of 2n squared, we can imagine what T4 might look like in its full form, and that might look like this. So T4 might be equal to something like 2n squared times c, which is a constant, and then some other terms. So here what we are saying is that whoever came up with this big O expression for T4 must have said that this term is the fastest growing term, tn squared times c. And then they must have said, okay, remove the coefficient c, and then we get tn squared as what should go inside the big O expression. And further, we might imagine what the rest of the terms might look like. In reality, we don't necessarily know, but as an example, they might look like this. So here we have 2n squared times c, which is the fastest growing term, and the rest of the terms must be slower growing terms than the fastest growing term. So we said, there might be something like c2n plus c3, where c2 and c3 are constants. And if you had something like that, 2n squared times c is going to be the fastest growing term. And that means that when n is large enough, this term is going to be much larger than any of the rest of the terms. But actually here, you might notice that you can rewrite 2n squared times c this way. So I just rewrote 2n squared times c as 2c times n squared. And looking at this way, the coefficient of the fastest growing term is not c, but it's actually 2c. So taking that off, you can say, well, n squared is actually what should go inside the big O expression. So T4 is actually of n squared. So what I showed here is that if we know that T4 is of 2n squared, it's actually also of n squared. And actually, of 2n squared and of n squared are technically equivalent. So technically, you could use either one to show that T4 is quadratic time, but by convention, we usually use the one with no coefficient attached to it. So in this particular case, that's of n squared and not of 2n squared, of 3n squared, or of 4n squared, even though they're all equivalent. Okay, and the argument I used here is not the most mathematically rigorous one, but it's actually good enough for all practical purposes. And that wraps up my introduction to big O notation and time complexity. This was actually part of my data structures and algorithms series, so just in case you want to check it out, I'm going to put a link to the entire series in the description below. Now, if you're looking for a more in-depth discussion,
Okay, that was a very good and detailed elaboration on how you use and calculate that big O notation. Can you understand that? I think it's very clear, right? Because after
Yeah.
this, after this few slides, there are a lot of calculation below. That's why if I don't show you that illustration on how to calculate that, it would be hard to understand what is actually big O notation. Okay, so I will give you these slides for you to bring back, for you to read at home. I'll give it to your email, and do find time to again watch that video, yeah, because a lot of the calculation later in the slide will have that particular example. How you find the big O, order of n, okay, and n squared, and then the other one is the constant value big O1, right? So those are how you compute efficiency of the algorithm. Okay, now back to this trade-off. A while ago we have the trade-off, right? That means this one, how you basically, usually a trade-off, how you settle between the time and space requirement of a program. Okay, so this one is that a trade-off is a situation where one thing increases and another thing decreases. It's a way to solve a problem in either in less time by using some space in executing an algorithm, or in very little space by spending a long amount of time to execute an algorithm. So like based on the example just now which you saw in some of the slides, it says that if you have a big input, therefore and then the time will be that it will be longer to execute that, and given time to respond, to get the response would be longer as well. So this is, I gave you an example of in a real life relation. For example, here the smaller code or loop unrolling, that means the smaller operation that you put in your code. Okay, loop unrolling means you reduce the iteration that you have in your code, therefore less memory it will consume. So when less memory, therefore less time is required to actually execute and get the result of what you wanted the program to give. Okay, so that is smaller code or loop unrolling reduced iteration. Okay, so that is an example of situation where one thing increases. If you decrease the code or the loop, then therefore a time for you to get back to the response time would be greater. Next one example is a compressed or uncompressed data. A space-time trade-off would be, space means the memory that you consume. Okay, can be applied to the problem of data storage, which is referring to compressed data or uncompressed data. You know what is compressed data and what is uncompressed data, right? Basically, if data stored is uncompressed, it takes more space it will occupy more space in your computer memory, and then but less time. Okay, because why less time to actually execute it? Because you don't have the time to spend so much on decompress it. You want to get back to the decompressed version, because you have already compressed it into a smaller compact version. So in order to actually execute it, it needs to be decompressed. So that takes a longer time. So if data is stored uncompressed, meaning the data will take up a lot of space, but it would take less time to execute it. But if the data is stored compressed, means compact, becomes smaller, it takes less space, but more time to run the decompression algorithm. Okay, so this is one example of a trade-off between time space. In a situation where one thing decreases, you decrease the amount of input, therefore the time to actually execute that becomes greater, more memory. Okay, so and vice versa. So this is just an example of time-space trade-off. Okay, next one. So goal for algorithm analysis is to basically achieve efficiency in data execution. So due to this shortcoming of experimental analysis, which we have gone through earlier, we need an approach that will analyze the efficiency of algorithm. For this one, you have three. This is basically an algorithm analysis goal. Number one, it allows us to evaluate the relative efficiency of any two algorithms in a way that it can be run without looking at whether or not that particular hardware or software gives problem. So that means to say that your program or your code is actually efficient in terms that you reduces any sort of sorts of complexity in the arrangement of your codes, removing the looping, for example, that would be one example. Okay, so then it can actually produce a better efficiency of running the algorithm. Number two is performed by studying the high-level description of the algorithm without need for implementation. So you check on the code by experimental analysis, and then after that you perform a studying of high-level description of the data, of the codes, of the algorithm without need for running or compiling the whole code. So this is done by checking one particular code depicted from the whole program as a whole. So you study one by one, then therefore after that you're able to actually come up with a solution saying that, okay, this can run efficiently and gives you the response time which are efficient, means less than when it is executed. So that is the goal of algorithm analysis, just to ensure that the codes which you have written down in your program is good enough, or you call it efficient in producing short time execution for getting the results. Yeah. So number three, it takes account all possible inputs. For experimental, you sometimes leave out some of the input because of time's consuming and all that. So for goal for algorithm analysis, you want to consider that you want to cover everything as possible, so that you are able to see whether or not all sorts of input that you test on that particular program return you the best possible efficiency that will be achieved by that program in terms of the result that you get. Short time, response time, and then efficient in giving you the output that you wanted. Okay, that is the goal for algorithm analysis. Okay, so time complexity. This is the chapter focus for this that we are studying. Hang on a second. I'll be right back. Yeah? Okay. All right. Now let's focus on this. Chapter focus will be is summary. The time complexity of algorithm usually more important than space complexity, because mainly when you want to run a program, you want to see whether or not you can execute that program, get the result as fast as possible. So rather than looking at the space, At most time, a programmer usually look at the time. Attention is paid to time complexity of the algorithm. Okay, so actual time needed for an algorithm is difficult to compute accurately. So therefore, in this case, you need to estimate the time for the best case, average case, and worst case of how that particular program performed. Now here, we actually express time efficiency as a factor of problem size. Problem size, yeah, that means when you want to search, in this example, a collection of data, problem size is the number of items in the collection that you need to go through. Each of that collection you need to go through and skim through to get to the one that you want. So if there are 100 million data in there, you have to still skim through until the end. Okay, so how fast are you going to skim through? How fast are you going to get to the result that you want is basically on time efficiency, focusing on time efficiency, looking at the best case, average case, and worst case. Okay, that will be explained in a second. I think I gave the example on that one. All right, so these are the terms which I give. The term best case performance, in the slides, you also have that explanation, but this one is maybe a simpler version. Okay, the term best case performance is used to describe a way an algorithm behaves under optimal conditions, best case scenario. So best case meaning the most optimal is that there is reduction in the size of the looping or whatever conditions that you have in the program, and then it performs optimally based on the response time, that it gives you the output that you want in less time. Best case. Average case usually requires that you calculate the expected running times based on a given input distribution. Okay, so basically you have a set of input and then you run it, you divide it, and then calculate that based on the average of how many inputs that you have for that particular time. That is average case. Worst case analysis is often a particular concern because if you know that that is a problem with your program, now you want to solve that problem. So therefore, you want to know how much time that is needed in the worst case to be able to see that you can actually finish executing the time. So how much is the time? What is the maximum time that you need to actually overcome that kind of problem? So that basically an issue. But this is actually says that is a worst case in analysis is much easier than looking at the average, because average you have to go through everything and then you have to divide that with the amount of data that you have gone through. Okay, and then find out the average. Whereas worst case is that you just need to know how long will it take to actually, what is the most maximum time that it can reach to actually execute that much of data. Okay, it requires only the ability to identify the worst case, then you try to find better algorithm to replace that kind of algorithm which is inside the code and solve that problem. So this approach typically leads to better algorithm because you have already analyzed that, you have found out that that is the worst. Therefore, you tend to make it better by changing slightly different, more efficient way of arranging your algorithm. So that basically making a standard of success for algorithm to perform well the way you wanted it to perform. Okay. Sometimes in this case, you say worst case is necessary so that you can find exactly how is the way to overcome that for better program, which gives you less response time, okay, better response time in execution less, and then that also doesn't consume much of the space. So good in space and also time. Okay, so that is what is best, average, worst case performance. Okay, counting primitive operation. To analyze the running time of an algorithm, you always have to look at the primitive operation that you have. What are the example of primitive operation in your code? Okay, so this is how you should see. You want to count how many primitive operation. What are those? Those are, you want to assign a value to a variable. That is number one. That is one example of primitive operation in your code, right? Number two is following an object reference. So you want to refer to which project, which object means you call the object and what you want that object to actually do. Okay, and then performing an arithmetic operation. Okay, each of your program has its own function, has its own logic data, therefore referring to arithmetic operation. Okay, so one of it is to scrutinize, analyze what is the running time for that particular arithmetic operation. And next one is to compare two numbers. You also involve this kind of arithmetic operation, where how you compare two numbers and come up with a solution. You need to look at what is the execution time for that primitive operation, which is referring to two numbers comparison. Next one, accessing a single element of an array by index. How many arrays, how many elements you have in your arrays determines how many times you have to go through and search through each of the array to find which particular element that you want. Okay, so how long does it take? Okay, so you need to actually go back to analyzing your primitive operation. That is accessing a single element of an array by index. How long will it take for you to find that particular element if you have to skim through the whole array elements in your array? Okay, next one is calling a method. In your program, you have methods calling, functions calling. Okay, so how long will it take for you to execute that or the program in the way that you arrange the function call or the method call? How fast can it get and return you that particular operation should you run the program? That is example of your primitive operation. Analyze running time of your algorithm. Okay, so you analyze this calling a method. Last but not least, returning from a method. So after you call a method, that method has been executed, and how long will it take to return back to the overall function of the whole program? Okay, so end of that method calling and then back to that main function. How long will it take? So all these basically you are trying to analyze the running time of an algorithm without performing your experiment. You pay attention to your primitive operation. Okay, these are your example of primitive operation. All right. Okay. Instead of trying to determine the specific execution of each primitive operation, simply say you basically want to count how many primitive operation you have inside your program. So you might have one big program, and inside that big program, you have a for loop, if and else loop, okay, calling of method, right? Adding up numbers, all those are primitive operations. So you might want to actually count how many do I have in this particular program, and then how many primitive operations executed, and use this number of how many primitive operation you have as a measure of the running time, which takes to actually execute the whole program and come up with the results. Okay, so first what I meant is that you count everything, all operation that you have inside your program, and then with that number, you know, for this much of operation or primitive operation I have, this is the running time of how I compute the whole thing, get the results. Yeah. So next one, this operation count will correlate to an actual running time in a specific computer. So here it says the number of primitive operations an algorithm performs will be similar or proportional to the actual running time of that algorithm, because each of that particular primitive operation has time frame on how it runs in the loop, for example, or time frame on how it will compute the operational of adding two numbers, for example. Okay, all those require time. So the number of primitive operations and algorithm performs will be proportional or similar to the actual running time of that particular algorithm. So that particular number of primitive operation determines the number or the length of running time to execute the whole program to get to the end results, which means for you to get your output. Are we clear?
Oh, yeah.
Yeah.
Okay.
Okay. So I am going to stop. I'm going to stop somewhere until the end of the time, yeah? And we can continue tomorrow. But I will go on until the end of the time, or until which I can go. Next one. Measuring operations as a function of input size. So to capture the order of growth and algorithm's running time, you therefore say that you want to associate function fn, the function of n is basically some value which is not determined, okay, with the algorithm. Okay, maybe it could be n is not determined. So function is determined by the number of n. N is the value that you set for your running time. Okay, so to capture the order of growth of an algorithm running time, so you associate that with this particular notation, function fn, with the algorithm. Okay, this function fn will characterize how many number of primitive operation in your function that are performed as function of the input of n. So basically fn denotes that there are number of primitive operation performed as a function, and the input of that particular operand, primitive operation, will be denoted as n. Function and n is actually how many operands or primitive operands you have in that particular program. So this function fn actually expresses that and explains that. Okay, so you put f function inside n will be the number of primitive operation you have in a function, in a program. Okay, so this one is how you put it. You describe it fn, right? Okay, so this one is basically the one which I have already explained. Difficulty of average case analysis. Maybe you can read this at home. Yeah, difficulty of average case analysis. I mentioned an algorithm may run faster on some input than it does on other of the same size, basically referring to the software and hardware you have. So thus we may wish to express the running time of an algorithm as a function of the input size obtained by taking average over all the possible inputs of the same size. You take all the inputs that you put in, and then you divide that with the total and multiply by the running time. Yeah. So unfortunately, say such an average case analysis is quite challenging because it requires you to define probability distribution of the set of input. You need to have a defined value, I mean a set value that basically put it into the average number that you need to divide to get the average. So that has to be constant. So that's why it says average case analysis always quite challenging, because you need to have the exact value of your variable in order to get the average. Okay, so that is a average case. Worst case, easier, because this is just you want to find the worst case scenario, which is referring to the ability to identify what is the worst case input, which is often that you see challenging. Okay, meaning I have this much of input which I put, and then like I am reached to the maximum situation where I am still waiting for the time to actually execute the program. But how long will that time needed to execute the whole bunch of input which I am going to test on that program? Okay, so that is, then you have probably determined that by testing one by one. And how are you going to actually solve that problem? Because you first are exposed to the worst case scenario. Because this is easier, it says here, because you already determined the worst part, okay, compared to average or the best case. So therefore, this approach typically leads to a better algorithm because you are able to then reduce or fix the problem, and therefore you get a better results. Yeah. So okay, read through on this one. Worst case. Now these are useful formulas. Instead of writing 1 plus 2 plus, okay, and the, n, you could write n times n plus 1 divided by 2. Okay, so these are formulas. Problems, analyzing efficiency of algorithm. Okay, I will stop right here. We will continue this one tomorrow. Yeah, 28, right? Because there are 50 other slides here. 2,
So
3,
tomorrow is lecture.
5. Pardon me?
Tomorrow.
Tomorrow is 9:30, was it?
Is tomorrow lecture, not practical?
No, practical. Tomorrow is practical and tutorial. But
Oh,
I'm going to do very fast on this one, yes? Very
okay.
fast. Yeah, so this is very fast because it's just pictures, right? Yeah, I don't want to get you, I need you to actually absorb the whole first slides first, because there's too much information, so that when you fully understand for now, tomorrow will be easier. Yes? Because this
Okay.
one is really, yeah, is actually trying to see what you have seen in the video. So starting from here, this is trying to analyze the efficiency of algorithm by looking at the algorithm. Okay, so here is A, B, C comparison. And then what is the problem with that? Okay, so analysis is done on that and gives the example of how it is. A, B, C, and then plotting of algorithm. This should be easy. Okay, and then you express your algorithm efficiency by big O notation. Remember just now that video about big O notation, how you actually compute and you actually put that big O notation symbol, namely the order of n, or you call it order of big O notation, okay, which is under linear, what do you call this? Linear search algorithm on the order of O. So order of n, where you have, how do I write that? You have 0 and then n. Yes, that is order of n, right? And then you have 0, that O in the bracket n2, you call it order of n squared, right? And then you have the constant value, where is 0 or O is outside, and 1 is inside, so that is constant. Okay, so we will stop here. We will go very fast tomorrow on this one, the half of the lecture, right? It's how many is that? 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13, 14, 15, 18, 19, 20. Very, okay, it's very easy. All right, that's done. Okay, so we will continue tomorrow. All right, and then also for your practical, you have 2 hours, right? Practical, we will look at the next question. Okay, we will look at the next question.
Okay.
Yeah, wait, just see which one is that. Next question. If you notice, right, I have actually posted a pre-practical question for your self-review. What is important of this one is that, let me see one question, yeah. This is a sort of like a revision for you on the theoretical part. Can you see that? For example. Okay. What are lists, stacks, and queues? Okay, any answer. And then you have considered that you're developing software centers to host karaoke and whatnot. Okay, and then read through that. So based on case study above, analyze how lists, stacks, and queues can be applied in the system. Explain with relevant examples. Okay, so that one is, this is purely theoretical, just to test yourself. Because now that you're doing practical, right? I'm not sure whether, because this one I've seen in the course leader basically gave it to us, and then I'm not sure whether this needs to be submitted for marking, but maybe you can attempt the one which are here. Yeah, I gave how many? 1A, 1B, 1C, and then 2, 3, and where's number 4? 4 and 5. Yes. So now we are basically under chapter 3 here. Actually, all those questions are very simple. It's all, what is the big O notation, right? So, and then describes the steps to derive the big O notation for an algorithm. So this one you learn in the video, right? How you derive the big O notation for that particular algorithm. So each of the algorithm practically has a way on how you label it to become big O n, big O n squared, big O1, things like that, yeah? Okay, so tomorrow we will continue with the lecture. So pay attention to this one as well, self-review. Check yourself, you can answer that, yeah? And then for your practical, this one, if you notice, I have posted the complete version. That means it is right from the beginning until the end. Okay, so we have done 1 and 2 previously. Okay, now we already have done this one as well. Stack applications. I see that you have submitted that, Noel. And Kelvin, I haven't checked. 3 and 4. Which one did we stop this time? I think we did this, right? Did we do this?
Oh yeah.
Yeah.
3 and 4. Right? We did that, right? 3 and 4. Okay, so this week we will continue with 5 and 6. Okay, 5 and 6. This one also very simple. I will post to you customer.java, post office sim.java. Okay, so you use that and then you construct this.
Okay.
This one is, yeah, okay, this one is like, which question is it? 6, 5, 6, 6 has how many questions? A, B, and C. Okay, so let's see. So basically, this one is a whole module that computes the counter number for staff. What is this? Post office. Yeah. So this one is the counter. You should be able to actually display all these numbers in the counter, respective counter 1, 2, and 3. So once this one is out, then what is the next number that will be here? Okay, sequential. Okay, that is actually 1AB 6, 5, 6. This one is easy. This one is 6 is quite challenging, I believe. A and B and C. Yeah, so we should be finishing that, I think. Yeah, for this week. Yeah, I think so. But don't worry, I'll give you a lot of time. I'll be giving you a lot of time to finish this, okay? Usually I give about 1 week plus to finish. Yeah, but if you have problems anytime, you can always WhatsApp, right?
Okay.
So as you know, after next week, we will be having a face-to-face. I don't know whether you prefer face-to-face, but I plan to do like a hybrid method. That means that one time we will go face-to-face, and then the other time we will go online, something like that. What do you think? Because pardon me?
Hybrid.
You prefer, because I feel like the cases of this pandemic is growing, right? So I feel the less exposure, the better. So we do maybe a hybrid classroom would be better. Yeah. So I want to plan to execute maybe first week we go online, face to face. The next week we go online, something like that. So during the online face to face, we discuss about the problems you have, and therefore you bring that homework and you do it during the online time. Then we next week after that we go for online, and then after that we go for face to face, something like that. 1 week face to face, 1 week online, hybrid. Okay. So all right. In that case, hang on a sec. Yeah, I cannot record this lecture actually, unfortunately. So I need to kind of, let's see, I need to take picture of this. Just wait for a second. Yeah, I need to take a picture of this. Paint. Okay, so far any question?
No.
No? Okay. All right, so if there is no, hang on a second, yeah. We stop on that one. Yeah, okay. If there is no question from you, we will stop here and then we will continue tomorrow. Was it what time is it? 9:30?
Yeah.
9:30. Yeah, 9:30 to 11:30. Yes. So I see you tomorrow morning, 9:30 a.m. to 11:30 a.m. Okay. All right. Thank you for attending. I see you tomorrow. All right. See you.